So this is another concept here that's really important, but a little hard to wrap your head around maybe. Enthalpy, which the symbol for it is capital H, doesn't mean it's for honors, is the total energy in a system. And what that means is it's how much kinetic energy there is, how much potential energy there is, which is a function of which things are bonded together and which things that are attracted to each other are how far apart from each other. You can just think of it as like internal energy in a system. And some things have more enthalpy than others. For example, if you want to convert ice to water, you need to add energy because the water has more energy than the ice, even at the same temperature, because of the potential energy. And that's why our reaction pathway for that looks like this, right? You have an increase of energy, and this energy that is needed is absorbed from the surroundings. Okay? Delta H is the change in enthalpy. It's called change in enthalpy, is the change in heat that occurs during a reaction. So heat and enthalpy are often used in as synonyms because heat is absorbed and it's converted into enthalpy. You can also say, like, delta H can be called the heat of reaction. So anyways, don't think of heat as just being exclusively about temperature here. Okay, what part of a reaction pathway diagram represents the magnitude of delta H? So I'm going to draw an endothermic reaction here. We kind of talked about this briefly before. So the change in enthalpy is the heat change that occurs in a reaction, okay? So it's basically the difference between the enthalpy that the reactants have and the enthalpy that the products have. This is delta H. Why is this part not included? Maggie? Good, because it's gained and then it's lost again, so it cancels out. So the only overall like net change or gross change, whatever it is this. Net. I think it's a net. Okay. Okay. So we can think of it as being equal to Q. This equation we'll get into more later, and there'll be different versions of it, but heat, enthalpy, and Q are both measured as energy, and so they're both measured in joules, or more often in kilojoules for H. Okay? So what does that mean then? If you have an endothermic reaction, like this one, like this one up here, will delta H be positive or negative? So with any change, you can think of it as being final minus initial. So here the final is up here and the initial is down here. So if you were to actually find that difference here, you would find that it was positive because the system is gaining enthalpy. Okay, so we'd have a positive sign for endothermic. From the system's point of view, energy is being gained. Conversely, for exothermic, the final is less than the initial. So if you did like 3 minus 10, you would get negative 7. So this will be a negative delta H for this one. And the system is losing energy. We'll go over this lots. Okay. So then how do we incorporate delta H into a reaction? So we show it like this. If this is a reaction we talked about. When hydrogen and oxygen get together, they make water, and we've seen this reaction in class with the balloon, and it's extremely exothermic. It creates lots and lots of heat, okay, as do a lot of combustion. This is combustion because of the oxygen. Okay, so when that happens, you basically generate water along with energy. Okay, so we can show the change in enthalpy, which is this, as either being basically like a reactant or a product, like you just added in, like, oh, we produce water and we produce heat. Or you can actually write next to the reaction, delta H of the reaction equals negative 483.6 moles reaction. So that's a kilojoules per mole reaction. This is a weird unit. We're going to talk about it a lot. Okay, so what does kilojoules per mole reaction mean? It means like 1 mole reaction for this reaction would be 2 moles of H2 combined with 1 mole of O2 to make 2 moles of H2O. So I can basically say 483.6 kilojoules of heat is released. So you're interpreting the coefficients as being like moles. Because I mean, you could have hydrogen and oxygen react and release 10,000 kilojoules if you had enough hydrogen and oxygen. So how do we standardize this number to this reaction? It's with the coefficients representing moles. 483.6, I'm just going to say that again. You could have, this reaction could produce 10,000 kilojoules of heat. if you had enough hydrogen and oxygen. We standardize the change in enthalpy as being the amount of heat released or absorbed when the coefficients represent moles. 2 moles of H2 and 1 mole of O2 create 2 moles of H2O. So I'm going to write it over here. 483.6 kilojoules of heat is released when either 2 moles of H2 react, you could say with just the right amount of oxygen or even with excess oxygen, like if H2 is limiting, and 1 mole of O2 reacts, or 2 moles of H2O is produced. Okay? Sometimes this reaction part is not included, but it's the same thing. Okay, we'll do some examples of that in just a minute. Well, yeah. Okay, so delta H reaction, delta H, you can ignore this or you can have it there either way, is an umbrella term. There's lots of different kinds of delta H's. So another example of an umbrella term would be like shapes, and then there's squares and rectangles and triangles, but they're all shapes, right? So delta H refers to any kind of chemical reaction, but you can have specific types of chemical reactions that have specific types of delta H, okay? Not my best analogy, but not my worst. Okay, so delta H is the heat released or absorbed when 1 mole, well in these cases, when 1 mole of a substance combusts. If I gave you the delta H combustion of methane, you would say if this is the amount of heat released when 1 mole of methane combusts. If I gave you the delta H solution, that would be the heat released or absorbed when 1 mole of a substance basically creates a solution. We'd say dissolves in water. Okay? Or I could say, oh, the heat of fusion is the amount of heat released or absorbed. In this case, it would be only absorbed when 1 mole of a substance melts, goes from solid to liquid. Okay? Okay, so a couple practice problems. Write the thermochemical equation for the combustion of propane. Okay, and this is the heat of combustion for propane. Okay, we are going to do states of matter, why not? Combustion, what's the other reactant? Emily Lee. Oxygen. Okay, Trevor, what are the products? Good, CO2, H2O. Liquid or gas is fine. Okay, let's balance it. 3, 4, 5. Okay. So I guess I could have written this a little more clearly to show the delta H in there also. Okay, the idea is when 1 mole of propane combusts, there's a 1 here, understood. 2,200 kilojoules of heat is released. We're not going to write per mole there because it already is part of the molar ratio. 2,200 kilojoules of heat is created for every 4 moles of H2O created, for every 3 moles of CO2 created, for every 5 moles of O2 reacted, for every 1 mole of propane. Okay, if I burn 2 moles of propane, how much energy would be released? All right, 2 moles of propane. We start with that, and then we need to relate with, this is just stoichiometry, we need to relate through our molar ratios propane to heat. Like if I said how much water would be produced, you would just write 4 moles of water on the top, but instead it's heat, but it's really similar, 2,200 kilojoules. Okay, so we got 4,400 kilojoules. Okay, same reaction. Go ahead and try this on your own, composite, and then check your answer. Okay. I could be getting these answers wrong, but oh, there's only 1 sig fig. That's annoying. All right, fine. 200. Okay, go ahead and try this one. This is just using a different molar ratio in our reaction. Okay, so it's just like another thing you can wrap into your stoichiometry calculations, your dimensional analysis.